Hello, and Chin Dobry. My name is Stanley Chi, and I'm a researcher at Stanford University. It's a true honor to speak with all of you today. I want to extend my deepest gratitude to the organizers for this wonderful invitation. To the patients and families here today, your strength and resilience are the true driving force behind all the progress that we make. Please know that you are the reason that what we do. At the heart of this community are patient organizations like this foundation. You are essential partners in our scientific work, providing invaluable insights, funding critical research, and pushing us to focus on what truly matters. You accelerate innovation, and I'm grateful for this chance to share my work and my hope with you today. We are truly at the dawn of a new era for genetic medicines. I believe in the years to come, in the next decade, many diseases that are currently considered incurable will be cured. Our mission as scientists is to accelerate that journey and to accelerate the scientific breakthroughs into clinical reality and in a fast way. One of the most exciting breakthroughs on this journey is a technology called CRISPR. You may have heard about that as a molecular scissors. Sure, it gives us an unprecedented opportunity to go into our cells and perform a genetic surgery and correct or modify our genes to treat disease. The power of this technology is not theoretical. In just 10 years, CRISPR went from a curiosity in the lab to a medicine that's treating patients. In fact, the first CRISPR gene editing therapy, called Casgevy, has recently been approved to treat sickle cell disease, offering a potential cure for a lifelong painful condition. And I want to say sickle cell is just the beginning. There are already more than a dozen ongoing clinical trials that are using CRISPR to treat a range of disease. For example, from cancer to cardiovascular disease, from neuromuscular disease to HIV. However, while gene editing is incredibly promising, major challenges remain. There is a huge gap that between the discovery in the lab and also the clinical use as a medicine in patients. And this gap sometimes is called the Death Valley of translation. Many excellent scientific discoveries and tools failed to translate to become medicine to treat the disease. Furthermore, the scope of the gene editing is frequently limited to disease caused by single well-known typo or point mutations in our DNA. To cross this death valley and expand the types of disease that we can treat, we need to move from a single tool to a complete toolbox. And my lab focuses on this technology innovation and how to translate these technologies into the clinics. Our goal is to break beyond what limits the gene editing, which is often great, but sometimes can be risky, and the other approaches such as RNA medicine, which are often too temporary. And we believe the future lies in a third approach called epigenetic medicine, which has great advantages compared to both gene editing and RNA medicine. So it's a third class of completely novel, safe gene therapy that we believe. So what is epigenetics? Think of it as a layer of control on top of our DNA. It tells when our genes should turn off a gene and when our gene should turn on a gene. And all these instructions have no change in our DNA sequence. And actually, many diseases are caused not by a DNA mutation, but by these on-off switches that are incorrect. I also want to mention here that if you think about when we get older or when our cells differentiate, it's not really the mutation driving it. It's these instructions, these switches on off that totally turn the aging-related disease into a devastating condition. By engineering the epigenetics, we can develop therapeutics that are potentially safer because we are not causing any permanent DNA mutations. And this approach is also fully controllable because we can control how much to dose and when to dose it. And finally, it's also very suitable for mutation that not agnostic disease, means the disease that's not linked to a specific mutation. And many diseases fall into this category. To do this, we had to re-engineer CRISPR. We essentially break the scissors and create a nucleus-dead CRISPR system, or dCAS. This dCAS protein can be used to guide the molecule to target any gene. Instead of cutting, it will serve as an anchor to deliver other functional protein that can be used to control the function of that gene, so-called epigenetic editing. Using this dCAS platform, we have built a versatile toolbox for epigenetic editing. We can, for example, precisely regulate gene expression in our cells in tools called CRISPR-I, CRISPR-A to silence a gene or to activate another gene. We can reorganize the 3D genome structure to make it as healthy as possible. And we can also develop the hypercompact CRISPR molecules for delivery more efficiently into the body. Besides DNA editing, we also worked on improving the RNA targeting because some diseases also link to RNA molecules. And all this provide an excellent toolbox in the lab. And for example, our plasmid DNA deposit to add gene has been requested by global researchers by more than 10,000 times. And many clinicians also start to adopt this for their biomedical research and clinical use. As an example, we use this tool to address a major hurdle in gene therapy, which is delivery. Many CRISPR proteins are simply too large to fit inside one of the best delivery vehicles that called AAV, which is a harmless virus, but it has a very small capacity for cargos. And that really restricts the delivery of most useful CRISPR molecules inside the body for treatment. And however, if we look at the nature has evolved many other Cas proteins, and some of them are very compact. And for example, the one shown here called Cas12F. But most of these Cas molecules simply do not work in human cells. That's how as a technology developer, we come in and we systematically re-engineered one of these tiny proteins, creating a new molecule that we call mini-Cas or Cas-mini. Through rounds of protein evolution and design in the lab, we were able to dramatically increase its activity and improve its precision, and while maintaining its very small size. At the end, we create a tool that is both tiny and highly efficient in human cells. The impact of this is immediate. For example, this mini-Cas technology made the journey from a lab tool into a clinical trial in just 3 years, as I will show you in the next slide, that the disease that we are targeting, called FSHD, is the first global precision epigenetic editing trial for treating a neuromuscular disease. This disease, FSHD, facioscapulohumeral muscular dystrophy, is a devastating condition that can cause severe muscle degeneration and a lifelong disability. And if leave untreated, people can also die from it. It has no cure for this disease. And FSHD is chosen as one of the first examples for our epigenetic therapy. That is because by nature, it's epigenetic disease. In healthy people, a toxic gene called DUX4 is kept off by epigenetic marks. So everything good there. But in patients with FSHD, these marks are lost, and the gene turns on and starts to poison the muscle, and leading to global muscular decay. Our therapy uses a mini-Cas editor that can be delivered efficiently into the muscle cells and restore those natural off switches. And we can silence the toxic DUX4 gene without cutting the DNA. I also want to mention that this is a one-time treatment and leads to, hopefully, permanent relief of the muscular decay. So as a permanent cure, it's not just like a temporary treatment, it's a cure. So this clinical trial run by a company that I founded, CRISPR Biotechnology, began earlier this year in patients and represents a new hope for these muscular dystrophy patients. And I want to say FSHD is just the beginning. We believe that this epigenetic editing approach can be applied to many other diseases. For example, shown here is a haploinsufficient disorders, and many diseases belong to this category. For example, the devastating Rett syndrome, which is a disease affecting the brain function in young children. And we could use epigenetic editing to turn on the healthy copy of a gene to alleviate the problem here. And there are other diseases, for example, metabolic disease, including obesity and diabetes, could be treated by epigenetics. We could restore the function of the metabolic enzyme genes in our body. And finally, we also believe that epigenetic editing will be super powerful to protect our cells from degeneration associated with aging. In the near future, we expect to see more epigenetic therapies for neurological disorders and other genetic diseases such as liver disease or heart disease and brain disease. And in the long future, these technologies could play a role in organ regeneration and treating age-related disease. And we think that is a super exciting future because that will completely renovate both research and the treatment of this incurable disease. Of course, this work is not done alone. It is a result of the incredible dedication of the students and the postdoc and staff in my lab, and our wonderful collaborators, and the generous support from our funding agency. The future of the medicine is not just about technology, it's about community. It's about scientists, clinicians, and families working together. I'm more optimistic than before that by continuing this partnership, we'll turn the immense promise of the new technology and new gene therapy into a reality for patients and families around the world. Thank you for listening.